constructed as follows. First, I would like to talk about introduction and historical data. Then I will move to O4 and difficulties that we have why we see only one event with both electromagnetic and gravitational band, and what are the chances to see it more in O4. And then to the instruments that we will have in near future and how it would help us to get more events with both in the gravitational wave and electromagnetic band. So the first, from 2015 with the start of advanced detectors, we could see the universe in gravitational wave band, and we also have three major detectors like LIGO, Hanford, Livingston, and Virgo, and CAGRA, which is now joining this network, and in near future we'll have LIGO India as a fifth detector. But this is the three main detectors that contribute to the discoveries right now. And if we look on the CAGRA joined on the very late of O3, which was cut short due to pandemic. You can see that there is a break in observing time. And now we started O4 recently in May. Virgo will join in a few months, and CAGRA already made a small observation, and then there are planned next windows for observation. But with when the first observing run start, we immediately get the first detection, which was a bit of surprise because we did not have the estimates of number of binary black hole mergers, good estimates prior to the start of LIGO. But what is important, what you can see is that localization, it was not very perfect. There was the astronomical community was looking for the EM counterpart. Of course, there was none because it was binary black hole merger. But with the O2, the second science run, we got a very interesting event, which was GW 1708-17, and it was first ever detection of binary neutron star merger. It was first event that we observed in gravitational waves and electromagnetic band, and it was also the first direct proof that neutron stars are associated with the short GRBs. Of course, almost all theoretical models assume that the short GRBs are a result of binary neutron star mergers, but it was a direct proof. It was also first kilonova observed, and we got a constraint on neutron star equation of state, constraint of the neutron star radius. Also, we could measure Hubble constant from gravitational waves, and by having the host galaxy and redshift, we could measure the Hubble constant. There was a wealth of discoveries connected with only one event that we could observe in gravitational wave and electromagnetic band. What is obvious but maybe important to emphasize here, that gravitational waves give us the information on motion of the mass in the source, so how the process started. Electromagnetic waves give us the information what was the outcome of the process. What might be interesting in the middle, that if we have the polarization of the short GRB, it would give us the intermediate stage, what was the evolution of the magnetic field in the source, but we do not have it yet. We don't have the tools to measure it. And we were very lucky with this event, because this event was the closest short GRB ever observed. So we could observe it in gamma, we observed it in first the gravitational waves, then follow observation by Fermi. We can see the start of GRB. And then about 10 hours later we got the optical data. We were able to identify the host galaxy easily, and then get the evolution of the source in time in different wavelengths. We get spectra of it. So this is the image of the galaxy, and the source is abstracted galaxy. working. And with those 3 detectors working, we got a very precise location. Even if we have only 2 detectors, like for example 2 LIGO detectors in Fermi, the area of locality, it would be much harder to get this, get the source, get the host galaxy. And everyone signed up for the LIGO labs were looking for this event to get it, to find if there is a electromagnetic counterpart to this. Okay. So if we look on the list of possible sources that we could observe in the gravitational wave detectors, so we have measures. So for the binary neutron star measures, we got one event right now, and the possible EM counterparts are the short GRBs or kilonovae. Or for black hole neutron star measure, the possible EM counterpart is kilonovae. And for binary black hole measures, we can think that there might be a EM counterpart if those 2 black holes, stellar mass black holes, merge in the accretion disk of the AGN. Then we might have some electromagnetic counterpart. But up till now, we only have one EM counterpart connected with binary neutron star measure. With the burst, we could have burst signals, we could have a supernova or long GRB, but it's unlikely. Maybe there is something that we did not consider yet. Okay, so let's go to see what we have with the O4. As you can see, we just started O4 a few months ago with 2 LIGO detectors. The LIGO detectors will be joining shortly, and the Livingston detector have improved sensitivity. It's close to 60 megaparsecs of the BNS range. Hanford is slightly below, but it should go to the same sensitivity. Okay, so if we would like to count for EM counterpart, how is that? The LIGO Virgo collaboration provide the infrastructure, provide the alerts to the astronomical community, to those cooperated telescopes, to allow it to search for the EM counterparts for the candidates. So basically we have the data streams from gravitational wave detectors, and then we use the different search pipelines, the BERSEC pipelines, the CPC, CWD pipelines, and then we build the event candidates from all of the pipelines. And we try to make the sky localization, the parameter estimation using DOP, bias star, or other. And then it's matched to see if the multiple pipelines got the candidate. And then we got the data quality report from detectors, and if the event is plausible, is there any glitches or something like that. And there is a public threshold cut, and then the alert is issued in this case. So this is how the infrastructure is constructed. And if we look on the timeline, what was added in O4, which was not present in the previous science run, was early warning alert. Because if we have the detector sensitivity improved, and if we have the coalescent binary, we could, and we are using CPC pipeline, we could match the template that is produced from post-Newtonian approximation to the signal before the measure. The more sensitive detector we have, then we can match it before the measure because it's sensitive enough. And in some cases, we could make the detection before the measure itself and make some sky localization and send it as an early warning alert. So before the measure, then the first preliminary alert sent. Second alert with better parameter estimation. There is also some human betting, and this might result in a retraction of the alert or initial alert sent. And with better estimation, the next alerts are sent. So how the alerts are classified? There are 4 major groups, which is the binary neutron star measure, black hole measure, or binary black hole measure. This is the classification or terrestrial, so if there is a chance of glitch or background constellation. This is classified based on the estimation of the mass from a signal. And of course, sometimes there is a flag for astronomers that if the object has between 3 to 5 solar masses, that it's a mass gap object. So it's above the limit of neutron star, but below the observed black holes. So how the alerts are being delivered? Because we need to send it to astronomers. There are 2 infrastructures used. The first one is GCN, which originated from the 90s. For those who try, when there was a hunt for GRB afterglows, so we have the instruments like SWIFT or Integral or Fermi that are searching for short GRBs or long GRBs, and then we have it transmitted to the network of to GCN center, and then to telescope that sign up for it to search for the candidate. And the newer version, which was developed for O4, which is schema, which is more advanced version to also for the future instruments like Vera C, Rubin Astronomy, Antares, which is the neutrino experiments, to wire all the information for the multi-messenger astronomy community. So this here the flow of information is much more complicated in GCN. So now the both channels are used, and the board for the message exchange service for multi-messenger astronomy allow to similar functionality as GCN to just send the information observations and the analysis by the teams. But as you can see, the most of the analysis, most of the submission is from the GCN channel, or it's from LIDAR detectors. What is important that when O4 started, the 40% of all GCNs that were transmitted, the circular, so observation made by the teams was connected to live alerts. Okay, so with early warning, the first test of the early warning was done on all 3 data. So it was tested if it would work, if we have enough, if it would work. Here we have the long signal from a binary neutron star measure, and in time when the signal, we are closer to the measure, the signal to noise ratio increases. So we would fit the post-Newtonian template to the signal and try to detect it. And the higher the SNR we have, the better estimation of the localization we could make here. So we can issue the alert with better localization, which is crucial for the astronomers, because the lack of Virgo detectors we could see from any direction, but the field of view of telescopes it's usually very small. It's 1 square degree, so even if we get the 10 square degrees, it's a very big field to cover. So the O3 data showed that it's possible, and there was 3 out of 5 alerts that were tested. We could send the information to the astronomical community at 30 seconds before the alert. So is it possible to use it by the telescope? If the telescope got it 30 seconds before the alert, to reposition the scope, that maybe to focus on the galaxy with the highest probability of occurring measure. And basically, if they are using the fast mouse, which is the direct drive mouse, it could be done. The revolution could take 3 to 4 seconds, and if the dome is fully open, you don't get the latency from the dome. Even with the large dome for the almost 1 meter telescope, the rotation of the dome is about 30 seconds. So those warning alerts could be used by astronomical community. Okay, but still, if we are thinking about the events that we observed prior to O4, we got about 7 events that might produce the electromagnetic counterpart, but we got only one up to now. So what are the problems here? And there was no even counterpart found in O3 for 6 possible events, but 5 of them were black hole neutron star mergers, and 1 of them was binary neutron star merger. The problem was, one of the factors is localization. In O3 we did not have a good localization. The detectors were not, the sensitivity of the detectors was much lower than O4, a little bit lower than we expected. This representative example of the events, those were retracted, but here we got a very large area to cover. But the other factor was that the first event that we observed was only 40 megaparsecs. So it was close, and the further the event is, the more fainter it will be. So this is so if we are at 100 megaparsecs, the event would be about 20 magnitude in red. So we need to have a telescope of the diameter of at least 60 centimeters, which is quite big. The 1 meter telescope could get. With neutron star black hole mergers, the possible counterpart is the short GRB or more likely Tidonopy. And Tidonopy for neutron star black hole merger is fainter than for binary neutron stars. So, and those events we observed from more than 100 megaparsecs. So they will be much fainter. It will be about 23 magnitude in R filter. So yeah, this is the localization. So what we need to get those events is to have a good localization, but also we need the reference images. Even we have good localization, but we have the telescope of the observation of the diameter of 1 meter. We will need to take the reference picture to get the event from galactic background. Because if we have a small field of view, we cannot scan the whole sky. But those these reference pictures we can get. We need to have 1 week later to make it, or we need the reference. We need to be lucky to have this galaxy scanned before by the telescope. So this is the 3 most important cases where we do not see it. It's hard to detect optical transient. But localization will be solved with more sensitive detectors. But what about brightness of OT and angular resolution? We need to have the reference image to subtract the possible OT from the galaxy. The idea, what comes here is the scopes that cover the whole sky, like ZTF or LSST. And if we have, because the ZTF will scan the whole sky within 2 days, but only up to 20 magnitude, LSST will scan the whole sky on the southern hemisphere in 3.5 days in 23 magnitude. What is also important is ML tools that are being developed for telescopes, because we could translate the image from one survey to another one and use the scan galaxy by other survey for the telescope that made this observation, and try to make the image differentiation to capture the faint source that we have for the galaxy. So ZTF started to operate at the very end of O3, and the visible depth in R band is 20.4 magnitude, and it's located on the northern hemisphere. It scanned the whole northern whole sky, visible sky, in about 2 days. And we should see some results from ZTF, some at least candidates for alerts in O4. And also because it has a fixed observing schedule, the other telescopes follow the ZTF alert to make gather additional data on the observed transients. The other very important tool that I would like to focus on is Vera C Rubin Observatory, also known as LSST. The field of view of this observatory is 9 square degrees, and the median for a single visit, the point 5 sigma consort depth, it would be 24 magnitude for our filter, which is very important for detecting kilonopy. Unfortunately, the first flight is planned on April 2025, so this is here. And location is southern hemisphere. So basically, we have on one hand, we have the ZTF in O4, but in O5 we got the Vera C Rubin Observatory on southern hemisphere. And also here there will be no target of opportunity. There will be scheduled at least in the first years of observation. But other scopes will follow the alert sent by Vera C Rubin Observatory. The scope and schema architecture would allow Vera C Rubin to send the alerts to community, to astronomical community, and then to follow the Vera C Rubin transients by others, and also to cross-correlate with data coming from LIGO, Virgo-Kagra network. So this would allow to make much more detection. For Vera C Rubin, it will be possible to detect the kilonopy from more than 200 megaparsecs, which allows the multiple detection of EM counterparts and gravitational wave sources. But the problem is that the first slide is just after O4. So we need to see the full synergy between the Vera C Rubin Observatory and LIGO-Virgo-Kagra network. We need to wait till O5, so it's 2027. The other instrument that might be interesting to get the full, to look into the short GRBs and binary neutron star measure is POLAR-2, which is scheduled to be sent in 2027 on the Tiangong-3 space station. This is the project that is a cooperation with China, Switzerland, Poland, and Germany under the United Nations framework with China. It was approved in 2019, and there was a first mission POLAR-2, which was on Tiangong-2, which allows the measurement of polarization from the GRBs. Unfortunately, this instrument was not observing during the GW1708-17. But low degrees polarization could be due to the evolving polarization angle during the GRB mission. And what is important, this instrument should have a very good localization of the GRBs. So if there is a GRB and if there is a gravitational wave event, we will get the localization. We should get the localization quite well. So because my time is ending, the one shows a few other questions that might be solved by looking on the data from gravitational wave detectors and electromagnetic observation. One thing is the kilonova population, because we have from only binary neutron star mergers, we have the few types of kilonomy and few mechanisms that is possible, but there is, but the question is what is the percentage of the mergers which dominate. Here we have the different scenarios, so if the two neutron star merge, is it going promptly to form the binary neutron black hole, or is it going to hypermassive neutron star or supermassive neutron star, or it maybe form a stable neutron star. In those two cases, there is a difference in luminosity. So this would provide the one question. The other one is, what is the opening angle of the short GR? Because if we have a lot of binary neutron stars mergers detected in LIGO, we'll get some estimation on how big is the opening angle. But with the optical observation, we can get more. Also, how the kilonomy is it isotropic in most of the case, the case are only in some. The other thing that we can measure if we have the data from gravitational waves and optical is measuring the Hubble constant directly, not with not have this would allow them more clear measurement of it. But there is far more open questions that we could get from observing the events both in electromagnetic and gravitational wave. So what we are looking forward is to see the more events in both electromagnetic and gravitational wave bands. In O4, which is 1.4 years, should bring the wealth of the detection in gravitational waves, but also some detection electromagnetic counterparts, since we have the ZTF working. And in O5 we'll see the synergy between the LIGO network and Vera C Rubin Observatory, which should yield much more detections in the both bands. So thank you very much. There's some
so are there any questions about this?
At the beginning you mentioned gravitations, burst events, supernova. And do I understand correctly that there is simply out of reach of the stereo cell detectors
yes, the problem with there are problems with detecting supernova by gravitational wave detectors. For the measures, we can compute from GR and using the post-Newtonian approximation exact templates. We can create the network of templates, and we can easily match. Matching filtering for getting the data, it's much easier than looking for something that is not modeled. We do not have the good model for supernova core collapse. It's very hard to make and consume a lot of computing power. And we do not have the good models for it. We could make some heuristic models like coherent wave burst pipeline, which in fact was working very good because it was the pipeline that detected the first gravitational wave event. It was working for binary black hole merger. But the other problem is that we need the core collapse to be asymmetric to emit and higher the asymmetricity, the more emission in gravitational waves we have. And so basically, if we have the supernovae in area close to our galaxy, we could detect it, but we cannot detect it from the megaparsec range, which would be really nice because then we observe. But nevertheless, I'm looking forward that we have such detection like that, because then we could look into the supernova core collapse from this data.
Thank you.
not, so let's